Okay, so let me present our speaker today to start this new seminars or start again this seminar joined with people from Isemat and La
Carla, no te
Laguna.
oímos.
No?
Yeah. We hear.
No,
we
perdón,
can hear.
perdón. Sí, perdón, sí te oímos, es que tenía apagado esto, sorry.
Okay. So I can start again, let me present Bartosz in these seminars joined with people from Isemat and La Laguna. So today Bartosz is going to give his talk about the reduction of contact manifolds. So Bartosz, we listen to you.
Okay, so thank you very much. Thank you very much for the invitation. So yes, today I would like to first of all sketch a little bit the history of the contact Marsden-Meyer-Weinstein reduction, which is the analog of the classical symplectic reduction by Marsden-Meyer-Weinstein. So first I will comment a little bit the history, then couple of approaches to the problem, and in the end I will present also some new results that I got. I'm sorry those people that are hearing this seminar once again. It's going to be very similar seminar that in Zaragoza, maybe apart from the last part of the talk. So the idea is that the talk is divided into 5 parts. The first and the second. In the first and the second, I will recall the basic notion from symplectic and contact geometry. Then I will move to the classical symplectic tools and techniques in reduction theory, and then I move to contact reduction, and the last part will be devoted to the recent results. So during this talk, I mainly focus on coorientable contact manifolds, which I will define, but you can keep in mind that all the results can be generalized to non-coorientable setting. Then the whole theory gets much more technical, but the ideas remain the same. Okay, so first of all, let me recall you the first definition, symplectic manifold. So what is a symplectic manifold? Symplectic manifold is a pair P omega, where P is a smooth manifold, and omega is a two-form that is closed two-form and non-degenerate. And if omega is exact, which means that it's a derivative of some one form, where theta is the one form OP, we say that the pair P omega d theta is an exact symplectic manifold. Okay, and we simply write P theta. And the main interest will be put on the exact symplectic manifolds, since we will be interested in a general case for contact manifolds. We have a covering that is that has it's a line symplectic, one homogeneous symplectic line bundle. Okay, so now when I will say symplectic manifold, I mean, if not otherwise stated, I mean the exact symplectic manifold. Okay, so as I said, the general setting is as follows: that we have a R cross action where R cross R cross is R without zero. So the general setting is that we have an action on on P. It's a Lie group action by multiplicative group. It's GL1R actually, and then if P, okay, sorry, and in here, if P omega is a general symplectic manifold, such that is one homogeneous, which means that if we take the pullback with respect with this action of symplectic form, we get S times omega for every S it's element of our Lie group R cross. Or equivalently, it can be written that the Lie derivative of the fundamental vector field associated with this action phi omega is equal omega, where this is the Liouville vector field, which is the fundamental, as I said, the fundamental vector field right, of this multiplicative Lie group action. Okay, so this is the general setting. Just to recall you, and we have that we define. Let me define an R cross principal principal bundle. So it is our principal bundle. So we have a projection from P to M with the R action on P with a homogeneous, define the one homogeneous symplectic form. And then we say that the triple P omega phi is a symplectic R cross principal bundle over M. Okay, so if we are in this setting, in general, what we get that we have principal, we have P omega, we have a R cross action, and then on a manifold M, we have a contact. We will get a contact distribution. But I will move to this later. So this is the general setting. In this case, we get, since omega is one homogeneous, in fact, P omega is an exact symplectic manifold. Since omega is closed, Lie derivative of omega equals omega, so one can easily, using the Cartan formula, I can easily show that this is an exact manifold. Okay, so the Marsden-Meyer-Weinstein reduction needs to presence of Lie symmetries. So now let us consider that on our symplectic the exact symplectic manifold, we have a Lie group action. So now we want that, since the Marsden-Meyer-Weinstein reduction uses the symmetries, so we want that our Lie group action is a symmetry of our action. So we say that the symmetry of our symplectic structure, or in this case, the exact symplectic structure, which means that leaves the theta form invariant. So we say that our Lie group action is an exact symplectic Lie group action if it leaves theta form invariant for every element G in a Lie group. Okay, so we have our symmetries. The next step in a Meyer-Weinstein reduction is we'll use the next step, the next tool that will be used in the reduction technique is the momentum map. So in general symplectic case, like we just the momentum map is the derivative of the momentum map is the contraction with omega. But in this case, we have the omega is exact, so we can define an exact symplectic momentum map and it goes from the manifold to the G star, where G star is a dual Lie algebra of a Lie algebra of our Lie group, and we defined it as the contraction of theta with respect to the fundamental vector fields related or associated with our action, and this is the pairing, the natural pairing between G and G star for every element in G, right? So and psi p, this is the fundamental vector field. The fundamental vector field associated with our Lie group action, right? So these are the vector fields that are tangent to the orbits of our action phi. Okay, so if you can easily retrieve the classical notion of a symplectic momentum map by derivating it and using that the Lie group leaves since it leaves the theta invariant, it leaves omega invariant, so you can manipulate formulas in such a way that you get the classical definition of a momentum map with minus sign, I believe. So yes, but since our symplectic manifold is exact, we use this feature and we use the momentum map using the one form theta. Okay, so the first difference is that in general case, our momentum map is not ad equivariant, but in our case, the momentum map is ad equivariant. And what does it exactly mean? Well, it means that if we have momentum map, we compose it with the Lie group, we get that this is equivalent to the dual adjoint action on G star. Okay, so in other words, sorry, it's we have the following diagram where here we have a Lie group action, here we have J, here we have J, and goes to G star, goes to G star. So this is the dual adjoint action to minus G to minus 1. Right, so on the pictures that yeah, it's sort of that. Okay, maybe. Yeah, maybe this picture. So here we have x, and this goes to J of x. This is G star. This is the symplectic manifold. So if we act on x by phi g, so here we are in phi g of x, and then we take the momentum map. So this is yeah, wait, this is related by the adjoint action. Sorry, it's this way. Right, so we can put here, and we move from here to here, but the dual adjoint action G2 minus 1. So in an exact case, this is always ad equivariant. The momentum, the exact symplectic momentum map is always ad equivariant, which in general symplectic case doesn't hold. Okay, do you have any questions? Okay, so another notion that is useful in the reduction technique is a symplectic orthogonal. Yeah, so the definition of symplectic orthogonal, sorry, is that when we take some vector subspace of our symplectic manifold, it doesn't matter whether it's exact or not at some point in P. So the symplectic orthogonal of the space W at P is denoted by this, and it is defined as all vector fields, all vectors in P such that the symplectic form taken on VP WP is equal 0 for all vectors in WP. Okay, so it reminds the notion of Riemannian orthogonality, but in this case, it may be misleading in the sense that it's not standard or intuitive notion of orthogonal vector fields or vectors. Sorry. Okay, so now let me move to the general reduction of symplectic manifolds. What I mean by general, I mean by reduction by a submanifold. So first of all, the assumptions are S is a submanifold of P. Okay. Second is that we have injective immersion of S into P. Then the kernel, because, sorry, what's the idea of the reduction? The idea of the reduction, let me first tell you about the idea, is that we start from an initial manifold P, and with the Lie group, or in this case it will be general, but with the Lie group action on it, and we want to find some quotient space that inherits the symplectic structure from the initial manifold. So this is the idea. So now the general setting is that the kernel of the pullback of omega into the submanifold S is of constant rank. The second is that the quotient space is a manifold. So I denote it by this. It's a manifold. And what is Fs? Well, Fs is a foliation on S given by the kernel of the pullback to form all the pullbacks of the symplectic form. Okay, and P from S to S to the quotient space is a submersion. Okay, so now the theorem is in this general setting. We get that the quotient space is a symplectic manifold and the relation of the quotient on the symplectic form on the quotient is with the initial symplectic structure is as follows. Okay, so we have a relation of the reduced symplectic structure and the initial symplectic structure, and moreover, one can prove that the kernel, which is the characteristic distribution of the symplectic form, I mean, it's not the initial symplectic form, but the symplectic form pulled back to S, is given by the intersection of a tangent at P intersected with the symplectic orthogonal for any P. Okay, and this will be very important, since by this theorem we know how to look for the characteristic distribution of a symplectic form pulled back to the some kind of submanifold, and in our case it will be the level set of the momentum map. Okay, so so what the classical setting of Marsden-Meyer-Weinstein reduction is when we so recall that we have a momentum map to G star. So let mu be J of P, and it will be weak regular value, just to make sure that the quotient will be that the level set will be a submanifold of P, and we take the S as the J of P. Sorry, not J of P, but the level set, since it has to be a submanifold of P. Take the level set, and what we get by this theorem is, the first of all, applying this general setting, and we have also a Lie group action that leaves the symplectic form invariant. So first of all, one can compute that the characteristic distribution of this two-form pullback to the level set. Here, J is the inclusion of the level set of the momentum map into P. So this is given by a tangent space to the orbit generated by G mu, where G mu is an isotropy subgroup of an element in dual Lie algebra. And in dual Lie algebra, we have an adjoint action. So it's G adjoint G2 minus 1 of mu that equals mu. So this is the characteristic distribution. So the second consequence is that the quotient space divided by G mu with omega mu is a symplectic manifold, and we have a relation that omega equals P omega mu, right? Where P is a projection from the level set of the momentum map to the quotient, right? This is the standard classical setting of the Marsden-Meyer-Weinstein reduction. Okay, so now the idea is to prove something similar, the similar theorem for the contact manifolds, coorientable contact manifolds. Okay, so basically we want to inherit the contact structure on the quotient. Okay, so let me introduce some basic notion from a contact geometry. So a general definition is that the contact manifold is a pair C where dimension of M is 2n plus 1, so it's odd, and C is maximally a non-integrable distribution of corank 1. Okay, so in other words, around any point in the neighborhood of any point X, we have that the contact distribution on U is given by the kernel of eta, where kernel of eta is some one form on this neighborhood such that eta, d eta, the wedged n times, doesn't vanish. So it's a volume form on U, and then we say that eta is a local contact form. So we say that MC is cooriented or coorientable contact manifold if eta exists globally on the whole manifold M, and then if MC is coorientable, we write just M eta. Okay, so there is a one-to-one correspondence between symplectic one homogeneous symplectic one bundles and contact manifolds. The general contact manifolds with a distribution. So yeah, there's one-to-one correspondence between the MC Yeah, 1 to 1, and one homogeneous symplectic line bundles. But in a trivial case, when the eta is coorientable, when we have eta, the correspondence is that we take P as the M times R, and the symplectic form here is defined as ds eta. Okay. And of course, this is exact symplectic manifold. So now you can see that why we will be mainly interested in exact symplectic manifolds.
You must change S by the exponential, because if no, when you
well,
take
okay,
S
sorry.
equal to, yeah. Sure.
Thank you. Yeah, it can be R and take an exponential of S, or we just remove 0 and yeah. Okay, so this is the correspondence in a trivial case. So again, we need to prove the analog of the Marsden-Meyer-Weinstein reduction in a contact setting. We need the symmetries. So a Lie group action on a contact manifold is a contact Lie group action. If it preserves, now, I mean, it can be generalized that it preserves the distribution, but for this talk, I assume that it leaves the contact form invariant. Okay, and then we can also define the momentum map, contact momentum map. Right, so since eta is a one form, so we can define it in a similar way as an exact symplectic momentum map. So we just take the contraction of eta with the fundamental vector fields xim for every Lie group, Lie algebra element in G. Okay, so the idea is as follows. So we more or less know how the reduction scheme looks in a symplectic setting. So and we know how to contact manifolds extend to the symplectic setting. So basically starting from contact manifold, where we have a contact Lie group action, and contact momentum map, right? So we prefer, since we know how it works in a symplectic setting, so we want to extend it to symplectic setting. It's exact symplectic setting actually. So we can extend the Lie group action on M times R in such a way that it doesn't affect the S coordinate, so it's just G of x, right? So we extend in a trivial case, in a trivial manner, and we do something similar with the symplectic momentum map. So it's S and X, and it maps to S times J of X, and it's of course in G star. And now, since J is a contact momentum map and phi is a contact Lie group action, so it follows that phi is a symplectic, exact symplectic Lie group action, and J is exact symplectic momentum map by construction of this extended Lie group action and momentum map. Yes. So now let me, before I move to the theorem, let me tell you about the history of contact reduction. So the first approach was made by Albert. It's C. Albert in 1989, and he devised the contact reduction in the sense that we start from contact manifold and we end up with lower dimensional manifold with also a contact structure. But in his approach, his approach has a couple of drawbacks. First of all, you can see that if we multiply the contact form by non-vanishing function in the sense of the distribution, it doesn't change, right? The kernel of eta and the kernel of f times eta, where the f is non-vanishing distribution, is the same. So we have here some kind of equivalence, conformal equivalence class of contact one forms. So first of all, his reduction depends on the choice of the one form within the conformal class, which is, well, one can say that it's not geometric, since for this we get some reduction 1 and we get reduction 2, and they're not equivalent. However, the initial contact structure remains the same. And then Christopher Willett, and one more remark, sorry. What is remarkable that this reduction works for every mu in G star. So then there were approaches to contact, many approaches at the beginning of 2000, many approaches to contact reduction, and people could prove that if we take the zero level set and we quotient the zero level set of a contact momentum map, and we quotient by the whole G, and this is contact manifold. Okay, and we, in the sense that it doesn't depend on the choice of the one form within its conformal class. So people knew that there has to be something, since this quotient, the analog theorem for the zero level set, holds as in symplectic Marsden-Meyer-Weinstein reduction. So then Christopher Willett generalized this reduction in the sense that, first of all, he takes his reduction works for any mu in G star, and moreover, the reduced space is independent of the choice of the contact form within its conformal class, provided that it is the initial manifold is coorientable contact manifold. Okay, so he generalized the Marsden-Meyer-Weinstein reduction for coorientable contact manifolds. However, it doesn't work in any case. Christopher Willett, I think it's 2002. He introduced a very technical condition which has to be satisfied to reduction if required. I mean, this condition is required to endow the quotient manifold with a coorientable contact structure. And well, this is suspicious, first of all, because in a symplectic analog of the Marsden-Meyer-Weinstein reduction, we do not have any condition this sort of condition. And the second observation is that this condition automatically holds if Lie group is compact. Okay, so he showed that if a Lie group that acts on a compact manifold is compact, then we have the compact Marsden-Meyer-Weinstein Marsden-Meyer-Weinstein reduction. Otherwise, he also provided a counterexample. If we take G SL2R, which is not compact, then this condition doesn't hold, and the reduced manifold is even dimensional, which is clearly contradiction since since compact manifold cannot be even dimensional. Okay, so how Wheelet proved his reduction in a case of compact Lie groups. How he generalized the fact that the quotient manifold doesn't depend on the choice of one form, so in a conformal class. Well, instead of taking the level set, he just took the pre-image of R cross mu, which is the pre-image is given by, so these are points in M such that the J of X is not mu, but something proportional, to mu, right? So here's lambda Rx. Okay, and then you can see that, well, if I denote it by the levels, the momentum map associated with eta, you can easily see that since that eta R cross mu is the same as J2 minus 1 F eta, where F eta is non-vanishing function. Okay, so this is using this idea, instead of taking the level set, taking the pre-image of an orbit. Actually, one can think of it. So we have an action on G star by S mu. It goes to S mu. So he takes the pre-image of this orbit for fixed mu. So this is how he generalized the contact reduction to still for coorientable case, but the reduced manifold doesn't depend on the choice of the contact form within its conformal class. Okay, so basically the theorem, Wheelet's theorem, says that first of all, we need to have this technical condition ker mu plus G mu equals G, right? Where G mu is the algebra of the isotropy group of G mu, and kernel of mu is, since we have the natural pairing, so this is psi in G such that psi mu equals 0. So first of all, we have also this satisfies all the technical condition that the pre-image of this R cross mu is a submanifold and so on and so forth. The quotient space is manifold. So he proved that the quotient by K mu, and I will explain in a second what is K mu. Eta mu is a contact manifold. Okay, with the natural connection between the reduced contact form and the initial contact form, right? Where P is a projection to the quotient HJ R cross mu into M. Okay, and what is K mu? Where K mu is a so K mu is one can show that this Lie subgroup with the Lie algebra K mu, and the Lie algebra of K mu is defined as the kernel of mu intersected with the Lie algebra of the isotropy group of mu. Okay, but what is important is that this condition must hold. Otherwise, the reduced contact manifold is even dimensional, so it cannot be contact. Okay. Yeah. So what's the how to fix it? I mean, how to generalize this theorem to also for non-compact Lie groups. So the idea is.
Sorry, Bartosz, I have a question.
Yes. Yeah.
And you mentioned that the manifold itself is independent of the conformal class of the form, but I guess the
Yes.
reduced form isn't, right? So eta mu.
Yes. So what's the question? Sorry.
Does it depend on the conformal class of the eta?
I mean, when you multiply the f by the non-vanishing function f eta, you just get f eta mu.
Okay.
Yeah,
so
because you're assuming if you change, I mean, if you change the eta, you just also have a change on the contact structure. I mean, the contact form basically, but the contact structure remains the same. But the manifold it's still the same.
Yeah. Okay. So changing by a conformal factor on the original manifold changes by a conformal factor on the reduced space.
Yes.
Right. Okay. Thanks.
It has to reduce, but if it reduces and then we multiply by a function that reduces, it of course also changes the reduced form. But when you start thinking about the contact structure in the sense of distributions, it doesn't change the distribution at all.
Mm-hmm. Thanks.
Yeah. So it's how to fix it. Well, the idea is to use the simplification. So we are in a setting of m times r, and we have a symplectic form as our cross story as eta. We have a Lie group action, right? We have a Lie group action tilde and symplectic exact Lie group action and exact symplectic momentum map, right? So I will call it d theta. And yeah, okay. So this is our setting. And why to move to symplectic? Well, first of all, we know the general reduction scheme by the theorem of the reduction by submanifold. And the second of all, in the symplectic case, the symplectic orthogonal is much more. I mean, it's easier to manage with the symplectic orthogonal with the not symplectic but orthogonal with respect to the d eta. Since d eta has a kernel, so it complicates things a bit. Okay. So in this setting, let me also introduce the following yeah, it's gonna be a Lie subalgebra. So maybe the theorem is that if you define G mu with the square brackets as the elements in Lie algebra, such that the adjoint action, I mean, it's adjoint map of mu with respect to psi wedged with mu, it equals 0, which is equivalent to saying that this is proportional to mu, right? And then one can prove that this is Lie subalgebra. And it has a Lie subgroup. Lie subgroup G mu with brackets. So then, right? So if we have a Lie group G mu, this is Lie subgroup. Okay, so the lemma for the reduction theorem is as follows. So now we introduced this space, this Lie subalgebra. So now we want to find the relation between the pre-image of R cross mu via momentum map and orbits of this subgroup and orbits of all groups. Right. So the lemma is as follows: the tangent space, the G2 minus 1 of R cross mu is given by the the symplectic orthogonal of the tangent space to orbit GP, at point P, intersected with the kernel of the primitive one form of the symplectic structure theta P. And now note that theta is nothing else than S times eta. I mean, of course, we have a projection, right? So it's a pullback of theta, to be precise. But the kernel of theta, the kernel as a distribution, it projects to the contact manifold, and a contact manifold that corresponds to the kernel of eta. Okay, and the second thing is that the tangent space to the pre-image of R cross mu, you're still in the symplectic setting. So now, in the second, we want to reduce everything on the contact manifold. So in the intersection of the pre-image of R cross mu, the pre-image of the momentum map of R cross mu, with the tangent space to the orbit at P, is the tangent space to the orbit at P generated by this Lie subgroup G mu in brackets. Okay, because here G mu, from the definition of the G mu Lie subalgebra, is that these are elements in G such that the adjoint action on G star mu wedged with mu is equal to 0, right? So it doesn't give mu as in the symplectic setting, but gives something proportional, lambda mu. Okay, and you can see that I said that the condition, in Wheelet's reduction, we have a K mu, right? So in our case, we'll have G mu intersected with the kernel of mu, and one can show that this is also a Lie subalgebra. So we have a K mu in brackets, and this is Lie subalgebra. It's a Lie subgroup, sorry. So the thing is that now if G is compact, if G is compact, then we get that K mu is equal K mu in brackets, right? So okay, so we get this, and if G is compact, it also induces this this condition. But if G is not compact, then K mu is a least subgroup of K mu. Okay, so that's why since it's smaller least subgroup that K mu in brackets, the quotient doesn't have the proper dimensions, since there are vectors, the vector fields that are in a characteristic distribution of, well, yeah, that in this case that are in a kernel of this extended omega, I mean the theta, that belongs to this, but not to this, but still are in the kernel of a symplectic form. Okay, so now, as you can remember, we take from the general setting, if we take J to -1 R cross mu, so the characteristic distribution, right, the kernel of omega, where omega here is d theta, is given by the intersection R cross mu with the symplectic orthogonal of this space. So what we get, sorry, symplectic orthogonal. So using this lemma, first of all, since we are on a symplectic manifold, the double symplectic orthogonal is the same. So we get that you get intersection R cross mu with GP and the kernel of theta at P, but this is dP of G mu of P by the second point intersected with the kernel of theta P. Okay, so now if P belongs to the G2 -1 R cross mu, and we take the, I mean the fundamental vector fields on P, but since the Lie group action is trivially lifted, these are the fundamental vector fields on them, but we're still in a symplectic sense, so a symplectic case. So with theta, well, at P, it's the same as J of P psi, right? So we have to have fundamental vector fields that belong here, but also are in the kernel of theta at P. So this is equal 0 if and only if psi belongs to kernel of mu, which gives us the tangent space of K to the orbit generated by K mu. So the general contact reduction looks as follows: that assuming these all technical conditions, I mean, sorry, maybe before I move to contact, now since we are in a symplectic setting, so we have that m times r is ds eta, r cross, sorry, ds eta, and it reduces, I mean, first of all, we have J2 -1 embedding of the preimage of mu, which by construction of this exact symplectic momentum map is, well, I'm a little bit the notation may be a little bit misleading, but this is r cross mu times r cross, right? So we project, and this is J2 minus 1 R cross mu by K mu, right? But K mu, the Lie group action doesn't affect the S coordinate. So it's basically R cross mu divided by K mu times R cross. Okay, and this is, well, one homogeneous symplectic, but the structure is S eta mu. Like, so this is the setting, and naturally after the quotient by R cross, we get that J to minus 1 of R cross mu K mu with eta mu is a reduced contact manifold. Right, where here the the pullback of eta is equal to pullback with respect to of eta mu. Okay, where here J mu and P mu is in a contact framework, so without tilde, M and P mu is the projection of, to K mu. And this reduction like work for every Lie group that leaves the contact form invariant. So recently there was also approach by like, I don't know, a year ago or 2 years ago, approach by Janusz Grabowski and Kasia Grabowska to generalize this reduction, the Willett reduction, to non-coorientable case. However, what they did, the characteristic distribution, since they work only on a one homogeneous symplectic line bundles, they find the wrong characteristic distribution, in the sense that the kernel of omega was given by K mu x, right? Which now we know that this holds only if G is compact. But they didn't include this condition by Willett, the kernel of mu of G plus G mu equals G. So the reduction, if we take the non, for instance, SL2R, which is all SL3R, which is non-compact, then the reduction doesn't work, since you get, for instance, even dimensional reduced manifold that was supposed to be contact. However, the ideas, including the treating of general contact manifolds as one homogeneous line principal bundles, is still applicable, and one can generalize all this setting, this reduction, to non-coorientable setting. Okay, so I don't know how much time do I have left.
In principle, minus 10 minutes, but I think
okay.
maybe
Okay, so no,
like 2-3 minutes or something like that, it's okay.
Okay, so what would be the next steps? Okay, so I'll comment only 2 things. What can be done further, and I will also relate to Marco Zambon's paper and I'm sorry, I forgot the name of his collaborator, but the paper is entitled Contact Reduction and Groupoid Action, and they present a very general approach to contact reduction. However, the approach differs since they study the lifts of the Jacobi manifolds, and they prove that basically that the manifold of this form has two is a locally conformal symplectic manifold or is contact manifold. So it differs in the sense that they didn't prove the contact manifold. They didn't give the recipe how to use the Lie group symmetries to get the quotient manifold that is always contact. They rather study the lifts of the Jacobi manifold, which is in this case the contact manifold divided by the whole Lie group G, and they prove that this leaves, which corresponds to the reduced manifold of this form, possess a locally conformal symplectic structure or contact structure. So it's a little bit different, and the approach is much more complicated and technical. Although the next steps is to, first of all, since in a symplectic setting, we have that if we take the pre-image of the adjoint orbit and we divide by G mu, is also symplectic. So one can also try to prove this theorem, analogous theorem, for in a contact setting. One can also look for orbit reduction, which is O mu divided by G, which is also symplectic. But in this case, the contact form, it's not only related to the initial. Sorry, in this case, symplectic form in here is not only related with the initial symplectic structure, but it also is related with the symplectic structure on an adjoint or on a coadjoint orbit. So it's more complicated. Yeah, but these are the ideas what one can do with it further. So yeah, that's all what I wanted to say. Thank you very much once again.
Thanks, Bartosz. I don't know if maybe there is some questions.
I have maybe one question. I don't know if Edith had one as well, or it seems like green. It seemed green the thumb. I don't know. Okay.
I have a comment. Yeah, so it's related with this last approach that mentioned Bartosz. So there is an idea. This is related with some Lichnerovi papers. The idea is that when you have the coadjoint action in general, you can produce a quotient coadjoint action on the Lie group on the sphere in the dual of the Lie algebra, or if you want, in the projective space. And the idea is that the orbit of this action are contact or locally conformal symplectic manifold. This is related with this approach and the Marcos-Ambon approach. In the Marcos-Ambon approach, when you take this last quotient in the slide, in the last slide by Bartosz, the quotient of the preimage of the quotient coadjoint orbit with the full Lie group, then you can obtain the two type of reduces space, contact and locally conformal symplectic structure. So this is the comment. This is this coadjoint. This is a comment that I want to do, because this approach to take the quotient coadjoint action and the orbit of this action, this is a result by, this is a loss result by Lichnerovich. So this is my comment, right?
Yes, thank you very much.
I had maybe a quick question, which is there an explicit description of the K mu that you described earlier? I don't know, in terms of like an equation or something, instead of being defined through the Lie algebra as the isotropic group is?
Once again, what equation? What sort of equation would like to get?
G mu, for instance, is defined as the isotropic group, right? So all those elements in the group, such that the coadjoint action leaves invariant the corresponding mu, right? And you defined K squared mu to be, or at least I understood, to be the associated Lie group to the Lie algebra K mu, which was the intersection.
Yes. Of G mu.
Yes.
Intersected with kernel of mu.
Yeah, I was wondering if there was some way of recovering this Lie group by a condition of the elements of G.
I don't know. Yeah, for sure it's a Lie group of G mu, but the elements of kernel of mu doesn't form a Lie subgroup, so it's not the simple. It's not such a simple introduction. It is intersection of something related with this, because it wouldn't be true. It wouldn't be intersection of Lie subgroups.
I see. Maybe with a leaf of defoliation defined by mu, something like
Bartosz, there is a question in the chat. Yeah.
Ruben, I have never. I mean, I didn't think about it before, so maybe I guess it can be somehow, but.
Okay, thanks.
But not in a simple way as on the Lie algebra level.
Yeah. I see. Thanks.
You're welcome. On the chat.
Yeah.
No,
I don't think so. It's equivalent to the Hergott's reduction. Yeah, it's I don't think so. I don't know what, because you are saying that the generalized nether theorem gives the contact reduction that I presented, or
I think that there are a dynamical approach of this reduction, of this contact reduction. In fact, Bartosz and me, during this week, study this kind of scene. What happens when you have a Hamiltonian, an invariant Hamiltonian function on the symplectic manifold, on the homogeneous symplectic manifold? What happens with the reduction of this dynamic, not only at symplectic level, but a contact level? So, but this is a project in progress with Bartosz. So this is the idea, and in this setting, of course, you have another theorem for the dynamics. So there is a classical result. It is related with the perhaps not with this approach, but this is closely related when you have a suitable submanifold of the symplectic manifold. Then, if you have an invariant Hamiltonian function on the symplectic manifold, you can transform the symplectic dynamics in rep dynamics. So, in this case, you can study the initial symplectic dynamics in the if you change the symplectic dynamic for the rep dynamics in the submanifold. But the idea is, from Bartosz and me, is to study what happens with the dynamics if you have symmetries and you apply reduction. This is the idea, right? But for sure, there is another theorem, not only if you have an invariant Hamiltonian function, for sure you have another theorem for the rep dynamics in the contact level. So this is the idea. I don't know if it is an answer of a part of the question in the chat, but I don't know what is the relation of Hergrove principle. I think that in some cases, Hergrove's principle is related with this kind of scene, but I am not sure if the Hergrove's principle is the right principle to relate it with this relation between symplectic and contact or rep dynamics of contact Hamiltonian dynamics. I am not sure. There are another possibilities. This is related also with a work in progress with the Edith and Sergio Grillo. This is Javier Fernandez. What is the natural variational principle when you consider this relation between symplectic dynamics and contact dynamics and another thing. So this is perhaps an answer a partial answer to this question, but it's interesting. Bartosz and me are very happy this week with this kind of with this kind of things, because it's interesting, of course. So.
Also regarding the dynamics, when you, of course, in this setting, you can consider the dynamics, and of course, if you have Hamiltonian, you have Hamiltonian contact Hamiltonian vector field. It's tangent to the preimage of this manifold. So when it's G invariant, it also reduces, and on the quotient manifold, you get reduced dynamics. And in the setting that Juan Carlos mentioned, when you start from a exact symplectic manifold with the Hamiltonian function, then you can of course take the level set. I mean, regarding that that the level set of the Hamiltonian function is a submanifold, and the Liouville vector field is transversal to this submanifold. You get the contact structure in here, and the Hamiltonian dynamics become rep dynamics. But using the approach I presented, the theorem, you can also you can define the momentum map on this level set, and you can, in the symmetries, if the Hamiltonian function is G-invariant, the Lie group action also descends to the level set of the Hamiltonian function. So you can treat as this level set as a contact manifold, and you can use the symmetries to get also sort of contact reduction for, in this particular case, for contact manifolds given by the level set of the Hamiltonian function. So of course it is related to Nether theorem, especially for it's of course it's related to Nether theorem. Yeah, but I'm also not sure what about Hergel's principle. So that would be a comment. Thank you.
Okay, thanks. I don't know if someone else want to ask. So if not, people from ISEMAT have something to say, or
I
we
don't
can,
think so.
if not, finish.